Okay, so the task I was given was to say something about the perspective of an applied mathematician, or the role of an applied mathematician in this grand business of uncertainty quantification. So Peter said a little bit about statistics, and we have this program going on at the moment where essentially applied mathematicians and statisticians are trying to learn from each other about the different parts of uncertainty quantification we typically obsess with. So I don't think it's a case that it's either we do things better one way and you do things better the other way. I think we sort of focus on different parts of the whole chain of uncertainty quantification. So what I'm trying to do with this talk is really, so that the title of my talk here is quite specific, Stochastic Finite Element Methods. So these are families, schemes of methods, computer models they could be called, specifically for dealing with models that consist of partial differential equations which have uncertain inputs. So Peter's already talked about this kind of complex modeling situation. But the thing that's kind of different for us is that we I should qualify this, I certainly can't stand here and talk on behalf of all applied mathematicians. I am a numerical analyst, and probably a lot of what I will say is coloured by the fact that I am a numerical analyst. But for us, it's really important what our computer is doing. We very rarely view our code as a black box. If you are from industry and we meet you at a study day, we'll typically bombard you with questions that you might not want to answer or not able to answer. What is your code doing? What are the underlying equations? What happens if you change the mesh? Can I change the mesh? Can I change these parameters? And almost always the answer to those questions are no. But I kind of, with this talk, what I'm trying to do is just perhaps sort of give you an insight into our mindset and also explain how many applied mathematicians and numerical analysts came into this business of uncertainty quantification in the first place. So it's more a sort of perhaps a historical meander into how this whole uncertainty quantification in applied mathematics sort of came about. That's my aim. Okay, some sort of background. In applied mathematics, those of us who train as applied mathematicians during our undergraduate degrees will typically be focusing on modeling things in the real world, physical processes that, as Peter said, are modeled by partial differential equations. So things like fluid flows, for instance. Fluid flow to the heart, for instance. Okay? So we typically take courses on these kinds of things, and the models that we sort of start from, we sort of believe. We kind of have a lot of faith in physics-based models. Newton's laws, we kind of believe those. Maxwell's equations, we kind of believe those. So we're usually starting from a point where we have models, differential equations that have been used for hundreds of years. They're not new in our community. So we're typically starting from a place where we have some equations that we trust, rightly or wrongly. Even those equations have typically been built with assumptions in there, but we typically just take our models as things that we trust. But okay, we know that we usually can't find the solutions to these problems exactly, so we're going to try and approximate the solutions to these problems somehow, and I'm going to focus on approximation schemes that are called finite element methods. They're quite widely used. And here's the killer. If we know all the things that we go into those partial differential equations, the geometry of the domain, the boundary conditions, the coefficients, the initial conditions, and so on, then we kind of have a whole field of approximation theory, numerical analysis, that we can use to get a handle on what errors we commit when we use finite element methods in our codes to approximate the solutions to those problems. But then we go out and we talk to people in the real world, in applications, in engineering, and they tell us, well, this coefficient is about this, but I'm not quite sure. So usually for us, this is kind of our first exposure to uncertainty. And so we need to do something. So one way to deal with uncertain inputs for our PDE models is to treat them as random variables, which sounds a bit odd, because in practice, in sort of a physical problem, they're usually not random quantities, they're just things that we don't know. But we can, or we do, typically, model things that we're uncertain about with random variables or parameters. So some of us taught the language of random variables, some of us taught the language of parameters. But if we put the inputs that we're uncertain about and we model them as functions of random variables or parameters, then our problem then becomes something that has a bit of a different nature, and we can't just use our favorite codes, our finite element codes anymore. We need to do something else, and this is what we mean by stochastic finite element methods. Okay, and there's lots of possibilities. So just a quick cartoon for the benefit of anyone who doesn't know what a finite element approximation is. That's fine. You don't really need to know for the purpose of this talk. The idea is you have a problem on some domain. That could be the table, your head, an aircraft wing, the whole planet. The way that a finite element code works is to put a mesh on that object, first of all. And the little pieces in this mesh are called elements. And what we do is we do in the computer code, we do local computations on each element. Okay, it's called finite elements. We do small local calculations, and we stitch all of those approximations locally on each element together to produce an approximation to a quantity of interest that's defined over the whole mesh. Okay, so what's special about finite elements? Well, of course, the number of elements that you've got is crucial to the accuracy of your computations. But the more elements that you've got, the more accuracy that you want, the more equations you have to solve, the slower your computations will be. So if we want an answer fast, that's no problem. We don't use many elements. But we're very fond of saying, how fast do you want the wrong answer? Okay, we can build cheap approximations, but the thing that we care about is balancing the accuracy of the computations with the speed of the computations. That's what numerical analysis is about. Okay, so types of uncertainty. When we all meet at events like this and we're all talking about uncertainty, we are typically talking about different kinds of uncertainty. So Peter has mentioned model uncertainty. So in applied math, I'm going to be honest, we typically don't worry about this very much. That's probably one of our biggest crimes. We take a PDE, this is our truth, and that's what we want to solve accurately. But we know that our models may be missing physics. We might be using an equation which assumes incompressibility of something, when actually we might know it's a bit compressible, but we've ignored that. So sometimes we kind of know, but sometimes we're just really forgetting about it. Parameter uncertainty, as I said, this is a thing that we sort of most often focus on, and the methods I'm going to talk about, this is kind of what they're designed to sort of take into account. We know that there's uncertainty in things that go into our PDE models, and we're prepared to think about that. And then we have, well, so some people would call numerical uncertainty the uncertainty error that stems from our choice of finite element approximation. What actually goes into your computer code? Okay, this is important. In applied math, we don't generally call this an uncertainty. We usually call this an error. And numerical analysis is all about this. Okay, what can we say about the error in the predictions that are coming from the computer models that we've chosen? So for us, this is not okay to forget about this, but we typically forget about this, and it's sort of like one crime versus another, right? So applied mathematicians, I would say, numerical analysts are typically, of course you might find some people who disagree with me, but the people I talk to and work with are typically dealing with these last two kinds of uncertainty and error. And we very rarely think about this, I think it's fair to say. We can also talk about the differences between forward uncertainty quantification and inverse uncertainty quantification. I'm sure this is going to come up later on as well. So I'm going to talk about forward uncertainty quantification. The methods I'm going to talk about, the computer codes, are designed to do this. You have a PDE model. You are prepared to model some of the things that go into that model with parameters or random variables. So what you do is you pick a sort of a probabilistic way of describing those inputs. You could pick a mean, a covariance, and some distribution information. Right? You have to decide how you're going to do this, and maybe you have data to inform you how to choose these things. You choose them, you put them into your PDE models, and then the goal, and this is, as Peter rightly said, is the thing that we frequently focus on, almost exclusively. We want to approximate a quantity of interest that's related to the solution of our PDE model, and we're going to use computer codes to do that. So the output of our computer code is going to be a prediction. We want to predict things. We might be interested in the expectation or the variance of the solution to our PDE, or the probability that something that depends on that solution is doing something interesting or bad. But we don't just want to predict a number. We don't just want numbers out of our code. What we want is this as well. We want an estimate of the error that we've committed in producing that prediction. That's kind of what applied mathematicians do, right? Okay, so just some quick examples to sort of These are all very academic examples. Just try and illustrate what I'm talking about. So here's a PDE model, right? In undergraduate mathematics, if you're doing fluid mechanics, you will meet this model. It's the Navier-Stokes equations. Okay, so let's say I needed to solve the Navier-Stokes equations. Okay, one important thing to get straight, this is a running joke in our program. What's the meaning of x and what's the meaning of y? In Peter's talk, x was an input parameter and y was the output. In applied mathematics, x is sacred, x is space, just like t is sacred to time. Okay, so x will always be a spatial point. Okay, so inside this model, the solution is a velocity and a pressure. But inside this model, this thing I've highlighted in red here is called the viscosity. In fluid flow modeling, this is really important because this affects the Reynolds number of the flow, the dynamical properties of flow, whether you get bifurcations, instabilities, and so on. That depends on the Reynolds number. So let's just put ourselves in a scenario, right? Perhaps an impractical scenario, but let's say I didn't know what the viscosity was exactly. It's about something, but we're not quite sure. So that parameter is uncertain. Well, okay, we could model it as something that's uncertain. So we could model it as a random variable or a parameter with a particular distribution. We might just know it's between A and B, so we have a range for it. So we might know a mean value, and we might want to build in a bit of uncertainty by adding on a variance as well. Okay, so the solution to this problem is now dependent on this random variable, this parameter. So the solution, the velocity and the pressure, is also uncertain as well. It's a function of that parameter. So I can write computer code. What I'm going to apply is a stochastic finite element method. And out of my computer code, I can get information like this. So I'm going to propagate the uncertainty in the viscosity through my PDE model and estimate statistical quantities of interest about the velocity and the pressure. So here I'm computing flow through a channel. This is called a backward-facing step problem. It's a sort of a classical toy problem. It's interesting because we get these recirculations in the flow, and we want to know about these quite accurately. Here you have an estimate of the expected pressure. And what can you see here? So you can hear there's this big spike here. So what's going on here? Well, this is just error. This is finite element error. My code was no good here, right? I kind of know this because I know something about finite elements, and I know that I have a lot of spatial error here in this prediction. That's information I need to know. I can also get out information like this. So not just a mean, I've got the variance. This is the variance in the speed of the flow. So red is the highest number and blue is the lowest number. So does this tell me where I'm most uncertain about my fluid flow? That's kind of one way to interpret variance, where the variance is highest. Well, this is the variance of the pressure. And again, I've got a spike here. The variance, or my prediction of the variance, is sort of high here. But actually, that's just spatial error. The fact that my variance is high there, it's not telling me that I'm necessarily got anything to do with the uncertainty. In some sense, it's just numerical error. Okay? So this is the kind of information you can get out of computer codes that apply stochastic finite element methods. Another quick example, again taken from fluid flow modeling. So these are a simpler set of equations. But the story is the same. We have a pressure field and a velocity field that we'd like to estimate accurately. And this is sort of a situation where we might be modeling fluid flow through a porous medium. So this coefficient A here represents the permeability of my medium. And this depends on space too. And I typically can't measure this everywhere. So here's a nice academic problem that I'm sure we might see in the workshop next week as well. We saw it in workshop 1, I think. So this is a sort of a semi-famous case study. WIP stands for Waste Isolation Pilot Plant. So in New Mexico, there is a place where they bury nuclear waste under the ground. And a couple of decades ago, they actually took some measurements. So this is a sort of a schematic which shows a geographical location, which is like 10 kilometers by 30 kilometers. And in this region, each of these black labels here represents one location in space where a physical measurement was taken. There are 41 measurements available. You can read the report. It's about 200 pages long, and you can get your hands on this data. Okay, so we want to essentially model fluid flow through a particular layer of rock in this region. And all we have to start from is, well, our assumption that we can model this with these equations. And second, that we only have access to these 41 measurements of what the permeability coefficients are, and that's an input that's needed for our model. That's something that we need in our finite element code. But we don't have it everywhere. So what is typically done, we use these 41 measurements and we do some sort of statistical crimes, and we come up with a hypothesis for a distribution for the permeability field across the entire spatial domain. So we then cook up, I do mean cook up, a sort of a mean, a variance, and a distribution. So what you're looking at here are two samples taken from a permeability which is treated as a random object, but somehow factoring into the decision about how I chose to model the distribution are those 41 measurements that I had. So given that information, I can sort of generate samples of A from the distribution that I've picked, and I can do Monte Carlo simulations. So Peter said, okay, Monte Carlo is not a good thing to do, so I'm going to go into a bit more detail about that. But this is the simplest form of stochastic finite element method. So when I say stochastic finite element method, I just mean that my computer code, the technology that's in there, is finite elements. Okay? What I do about the random part or the uncertain part of the problem is my choice, and that's what distinguishes between our different families of stochastic finite element methods. So Monte Carlo is the simplest, naive stochastic finite element method. So what do? You just generate lots of samples of your input, that's the permeability field in this case, and you run your code for each sample. Okay? Peter talked about his emulation. First of all, you've got to run the code at some choices of your input parameters. In Monte Carlo, we just randomly choose these. So I've solved the fluid flow equations for each one, and then for each of the velocity fields that I get out, I track the path of particle that's released into the flow here. So you can see I have a lot of variability. There's about 300 simulations here. And I leave my computer running for several hours, and what I get out is a prediction for the mean flow field. The mean flow field, and once I've got that, if that's what I'm interested in, I can now track the path of that particle within the mean flow field. Get an estimate. It's an estimate. Is it accurate? It's a pretty picture. Is it accurate? This is what the applied mathematicians, numerical analysts care about. I can plot pretty pictures, I can compute numbers. How do I in any sense know that's telling me anything accurate, right? How fast do you want the wrong answer? Okay, so Monte Carlo finite element method. So let's just review the main steps. So what do? This is the simplest thing. And I work with people in industry, and this is what they do, right? Not solving these problems, other problems, which are more complicated. So what do? It's a black box strategy. So we choose a statistical model for our uncertain inputs, whatever they are in the model. We use random field or random number generators to create samples of those inputs. So in this example here, that's what I had to draw, samples of my input. I run my finite element code as a black box to solve the flow equations or the PDEs for each sample. And then what do? In the Monte Carlo approach, we just average the results to obtain estimates of the quantities we want. So if it's a mean or a variance, we just average our outputs. Why is this done? Okay, well, we can just treat our computer codes as black boxes. People say, or at least in the math community, it's trivially parallelizable, as if nothing else is. And of course, there's no complicated mathematics. That's not to sound patronizing, that's just to say, if you're not a specialist user, this is attractive. I'm working in an industry where people have developed these codes, and we've invested a lot of time and money in these codes, and I want to use them, and I don't want to mess with them. So if that's the case, then you can certainly do this. So what's wrong with Monte Carlo? I think we all know what's wrong with Monte Carlo. It's very slow to converge. But I want to emphasize what's wrong with Monte Carlo from an applied mathematician's perspective. Where are we coming from? As I said, for us, it's all about accuracy. So very, very simple scenario. Let's say all I was interested in is estimating the expected value of something, U. So U is the solution to my real PDE. Okay? Forget about the fact there's the real world as well, but just the expected value of the true solution to the PDE. What I'm actually computing is this quantity here. So what is this? So if yi, so Geordie's favorite phrase, yi, if yi is my ith choice for my input parameters, so by choosing I create one sample of my input parameters. I run my finite element code as a black box to get this quantity. So this is now not U evaluated at yi, this is UH evaluated at yi. So h is usually the notation we use to remind ourselves there's a mesh behind the scenes when we use a finite element code, and h is like the size of the elements that we've used. So small h means better accuracy in general. So we do this m times, m is the number of samples, and we average, and this is our Monte Carlo finite element estimate for this quantity. Of course, so we do a bit of maths. This is a bit hand-wavy, but essentially we add in the finite element solution and we take it out again. And the error, that's what we want to control. How good is this thing as an approximation to this thing? Well, do some tricks. Well, the error is bounded by the sum of two terms. Okay? There's really two terms in the error. There's the error that comes from our computer code, from our finite element discretization, and there's the error that comes from estimating an expectation through a simple Monte Carlo type sample average. And when people say what's wrong with Monte Carlo, this is typically the thing that they're talking about. Right? This error goes like 1 over the square root of the number of realizations. So this goes to 0 very slowly in terms of the number of samples m that you're taking. If you treat your computer code as a black box, you don't worry about this. Okay, so what is this? H, as I said, is telling you something about the finite element mesh that you've used, and there's some parameter here, alpha, which will be extremely problem dependent. So you'll make an error, which will depend on your problem, the nature, the structure, how complex it is, and the finite element mesh that you've chosen. So what does that mean? If you have a computer code in which the mesh is fixed, right? You're treating it as a black box, you're not messing with it, you can keep drawing more and more and more samples and watch something converge, but you're only converging to something that has spatial error in it. Okay? If you fix your mesh and take more and more samples, you're not doing anything about the spatial error in that approximation. It's there. You'll converge to something and you'll get a pretty picture, but you haven't addressed the fact that this is not giving you the true solution to your PDE. And vice versa. If you only do a fixed number of samples and then you refine your mesh, then you're not going to do anything about this error. So what we want when we use this kind of method, and I'm stressing here, in solving PDE models, right, and using finite element technology, what we really need to do is balance these two sources of error. Because at the end of the day, this is what we want, and this is sort of at the heart of a lot of numerical analysis and a lot of applied mathematics. We want to make sure that when we do computer predictions, we can ensure that the error that we make in our predictions is guaranteed to be below some error tolerance. 10 to the minus 3, 10 to the minus 6, whatever it is that you want to impose. So as the user, you supply this, and then our job, as we see it, is to give you a scheme which guarantees you this. So if we were using a Monte Carlo finite element method, how would we do that? Well, there's two sources in our error. We'd have to make them both small enough in order to achieve overall accuracy that meets this condition. Okay, so this is just a sort of a quick back-of-the-envelope calculation. If you're not used to this notation, don't worry about it. But there's really two things that we control when we do these experiments. We control the number of samples that we take, and we control the finite element mesh size. If we want to balance out the two terms in the error, we have to choose them both proportional to the tolerance in this way. Okay? But then we think about cost. How fast do you want the wrong answer? We care about cost. When you apply a Monte Carlo method or any sampling method, you do a certain number of samples, that's m. That's how many times you run it. And then you have to solve a finite element problem. So when you are using a finite element method to solve a PDE, the finer your mesh, the more accurate it is, the more work you have to do. So how much does it cost in general to run a finite element code? Well, it's something, but it will scale like h, where h is the sort of the size of your mesh, to minus some power, which will depend on things like the spatial dimensions. So if you're in 3 dimensions, d would be 3. If you're in 2 dimensions, d would be 2. So then if you say, okay, what does it cost me to implement the method in such a way that I can compute my approximation and honor this? Well, I stick those two things in here, and this is what I get. The cost grows proportionally to the tolerance in this way. So tolerance to the minus some power. So what is that? Well, this power will be problem dependent, but let's just take the simplest academic toy problem of all time, right? The toy elliptic problem that we'll hear a lot more about next week, no doubt. even if I were to solve this very simple elliptic PDE, 2 dimensions in space, with linear finite elements, I can say what that is, the cost grows like tolerance to power minus 4. So what does that mean in real terms? If I decrease my tolerance by a factor of 2, I have to do 16 times more work. If I want one more digit of accuracy, I want to reduce this by a factor of 10, that's 10,000 times more work. Okay? So the important thing, not to be patronizing, is this isn't the only thing that kills you. When you factor in the cost of the computation that you have to do in order to achieve this, it's a much bleaker picture. Okay? So this is really the motivation over the last couple of decades for people in the applied math and numerical analysis community to really try and do something better, right? Try and do something better. Okay, so there are many alternative methods that rely on existing finite element technology and that can be used around existing finite element code, right? So there's going to be lots of talks about all of these kinds of things at the upcoming workshops. A lot of people in this room, the academic members of this community, are experts in all of these things. I am by no means at all an expert on probably any of these things, but this is just kind of giving you a sort of... One thing that we've learned over the last few weeks is language is very important. And one method that's known by one name in one community is known by another name in another community. So, in the applied math community, these are the kinds of labels and language that we use. So if you're looking up papers and things like that, this is kind of the keywords to look for. So Monte Carlo methods obviously have a role to play and are very attractive when you have to just reuse black box codes as they are. But naive Monte Carlo sampling, we know, we've moved on a long way since then. Nowadays, there's a lot of work in multi-level finite element methods, multi-fidelity Monte Carlo methods, and multi-index finite element Monte Carlo methods. So if you have the ability to run lots of different models or the same model but on a hierarchy of meshes, you can often accelerate Monte Carlo computations quite a long way. Stochastic collocation methods, reduced basis methods, stochastic Galerkin finite element methods. These are all methods that rely on existing finite element technology but do something different in the way that they handle the parameter dependent or the random part of the problem. So I was going to say a few words about a couple of these methods. I do have a few minutes left, do I? I think. Okay. Well, so a couple of things that I just wanted to highlight. So I should say my slides will be available at the end, and there's lots of references at the end if you want some academic references for some of these methods. So the two I've highlighted in red here, stochastic collocation finite element methods, stochastic Galerkin finite element methods, are sort of based on a different kind of philosophy that you can approximate the solution to your problem as a function of the parameters that you're uncertain about, and we model the dependence on those parameters in terms of polynomials. So in some parts of the community, the term polynomial chaos methods is used. That's just a certain kind of polynomial approximation. And the thing I've highlighted in blue is quite trendy in the applied math community at the moment. Reduced basis methods, I think, are quite attractive for anybody who does need to work with black box codes because they can be wrapped around existing sampling sort of scenarios quite easily. So I just wanted to pick on a couple of these methods to just sort of describe in a very sort of high-level way sort of what's involved if you want to do the computations a slightly different way. So let's start with the idea of something called the stochastic Galerkin finite element method. Okay? So we've got a PDE, and U is the solution to our PDE. Our PDE's got some uncertain parameters which we'll call Y. So in this kind of approach, what we do is we approximate the solution to our parameter-dependent PDE using an expression that looks like this. Now, if you are someone who's used to finite element code and you know what finite element code does, then this should be completely natural. The only difference here is that we are representing the solution or approximating it through an expression that depends on our parameters. So these will be chosen to be polynomials in our parameters. This is the kind of approximation scheme that we use. These functions which depend on x will still be finite element functions. So we'll still be able to use our finite element code to generate an approximation of this form. So what happens if you were to code this up yourself, if you had the ability to do that, what you'd have to do is solve one very large linear system of equations to get this information. The problem, of course, is that unlike in Monte Carlo, where you're solving lots of different finite element problems one at a time or in batches, here you just solve one problem, and the size of that problem is the number of polynomials you want to use in this expression, that's n in blue, multiplied by the size of your finite element problem. So it's some times bigger than the finite element problem that your standard computer code would solve. And that's the main work involved in implementing these methods. But what comes out of these simulations? We don't just compute samples of the solution. No sampling is going on here. What we're doing is producing a functional approximation of the solution to the PDE. So what we get when we've solved this problem is this information, the terms that go in this sort of expansion of the solution to our problem. So we don't get samples of the solution as the output, we get pictures like this. So this is going back to that fluid flow problem at the beginning where we had flow over a step and we had a recirculation here. When we use this kind of approximation scheme, we get these functions. These are functions of space. So these are all functions that represent my parameter-dependent solution to my PDE. And with this information, I can go back and estimate quantities of interest related to my solution quite easily. Don't have to do any sampling. So in this particular example, for instance, vorticity might be a quantity of interest. I can get that quite easily because I have a functional form for my approximation. And okay, a more specific quantity of interest, I might be interested in the integral along some part of my boundary wall of the vorticity. The vorticity is a function of the fluid flow is a function of this parameter. So if I wanted to know sort of the distribution of this quantity of interest, I can do that now simply by exploiting that functional approximation. And as with Monte Carlo, where we're controlling the accuracy of what we're doing in some sense through the choice of finite element mesh and the number of samples, now we still have to choose a finite element mesh, but we also have to choose the number of polynomials in this approximation. So it's a different kind of approximation. And as we use more and more polynomials, our approximations become accurate, we see them convergent. But again, it's the same story, okay? Pretty pictures, numbers out, what can I say about this? So the methods are there, but a lot of the people here and a lot of the talks that will be around next week will be about, well, do we trust these numbers? What can we say about these? We need some error analysis that tells us how good these approximations are to the solution to our original PDE model. Okay, and then just a couple of quick words about, I'll wrap up in 2 minutes. Another strategy, reduced basis finite element methods. Now, in talking to some of the statisticians the last couple of days, I kind of realized that statisticians do this as well. They just use a different name. So I think probably the name is something like surrogate modeling, but this is a sort of a general strategy to compute cheap surrogates, I think. So this is quite appealing if you do want to do sampling. If you just want to use your black box finite element code with certain choices of input parameters. So let's have a look at this. So what happens if you use a standard finite element method? And again, just to stress the importance of language. In this community, this term is often used, high fidelity method. High fidelity means sort of you've got good accuracy. So if you want to apply a standard finite element method, here's your solution to your PDE again. This is a thing that you never have. In the standard method, you're going to approximate the solution by choosing a finite element mesh. So we have our H here. For each choice of samples that you might be interested in, so if you're doing Monte Carlo, you're going to generate samples of these things. For each choice of the sample, now you have to solve a linear system of equations. That's what's at the heart of any finite element code. That's where the bottlenecks are, typically. And the size of the system that you have to solve depends on your finite element mesh. Okay? So if your finite element mesh was always fixed, then you probably know how long each run of your code takes. But if I change the mesh, this time changes. So if you want to do Monte Carlo using M samples, okay, that's the only thing you can do. Okay, but let's try and make it a bit better. You have to solve M problems, okay, so you might be prepared to live with this, but what you'd really like to do something about is the time it takes to solve this system, the time it takes to run your finite element code. Okay, but you don't want to sacrifice the accuracy that's afforded by the fact that you've got a mesh with size h. So that's the key. can you implement this in such a way that you can do it cheaper but still get the same sort of spatial accuracy that you'd like? So here's what's typically done. Instead of trying to compute the finite element solution for lots of different choices of y, you're going to come up with a surrogate which we'll call UR, R for reduced, which will belong to a much lower dimensional space than the original finite element solution. Okay? So a finite element solution lives in a very high dimensional space because the basis functions are associated with a mesh. The finer the mesh you have, the higher the dimension of your approximation space. So here's a general strategy in key terms. So if you are a user of code, you can think about whether this is easy for you to do or not. You run your expensive finite element code nr times. Okay? Here's the black magic at specially chosen sets of your input parameters. That's where all the theory is. You then collect the solution vectors into a matrix. You make them the columns. Again, language, we call these snapshots. So these are individually different finite element runs for different choices of the input parameters. You collect them together, and then you do a bit of manipulation on this matrix. You create a new matrix, which we'll call our reduced basis matrix. Now, this needs to be what we call a tall and skinny matrix. So this dimension will be the size of your finite element mesh, and this dimension will be the number of runs that you've done. We're only going to get savings here if nr is much smaller than nh. So we do this, we generate this matrix, and then what we do is we just project our original problem down onto a smaller dimensional space. So basically, if we want to generate a sample of our solution for any particular choices of input parameters, maybe we're doing design, optimization, something like that, right? I want to quickly query my finite element solution for lots of different choices of my input parameters. If I've got this matrix Q available, if I've done some time to get this, I can then compute this thing called UR, which will be our reduced approximation, by solving a much smaller system. So the original system had a matrix A, which is of size NH. This matrix has got size NR by NR. So if you did 10 model runs, this is a 10 by 10 matrix. Okay? And in this sense, very similar to some parts of what Peter said, we can do this quickly. If NR is 1, it's cheap. If NR is 10, it's cheap. If it's 100, it's cheap. Finite element meshes are usually many hundreds of thousands, if not millions, of degrees of freedom. So we can solve these problems much, much quicker, and then we can plug these into any sampling method that we want to use. So here's just some academic examples. So here's again a fluid flow problem through a geology that looks like this. It's got 5 different subdomains. The permeability coefficients are uncertain in each region. So we've got 5 uncertain parameters. And the finite element method has got 217,000 degrees of freedom. So if we use a standard finite element code and we put in one choice of our input parameters, we have to solve a problem of that size. So here's some timing. So just focus on this column for a minute. So this is 2 seconds. That's actually not expensive. So each model run costs 2 seconds, right? So not 6 hours, but 2 seconds, okay? If you're going to do naive Monte Carlo and you needed 1 million samples, that's still 2 million seconds, right? So what can you do with a reduced basis strategy? So you spend some time constructing your reduced basis first, and then you can solve a reduced version of the problem. So this is the time it takes to solve the reduced problem. So you should be able to see that these times go down by orders of magnitude. But I want to stress, we can make this as quick as we like. What we want to do is implement the method in such a way that we can guarantee a certain level of accuracy. So as I am asking for more accuracy in my method, the size of the reduced basis that I need to meet those accuracy requirements has to grow, and so these timings will ultimately grow. Okay? So in all of this, there has to be a consideration about accuracy, because I can always cook up a cheap surrogate that's quick to evaluate. So in applied mathematics, this is the kind of information that we're interested in, always balancing cost against accuracy. Okay, I think I will perhaps skip that and just skip to my conclusions. There's a lot of information there. I kind of really only wanted to present some sort of, at least some exposure to some methods that are out there. And these are the 4 sort of take-home points I think. Applied mathematicians, most of us, are mainly concerned with the accuracy of outputs of computer models with respect to the true solution of the continuous PDE type model. Okay, we think this is really important. How fast do you want the wrong answer? This is what we bang on about. But alongside that, we often are guilty of not paying enough attention to the real world and trying to quantify the error between the real world and our PDE models. Okay. Standard Monte Carlo, we know, is infeasible, but just to stress, this is the thing that's actually kick-started a lot of work in our community. This is what we're trying to do better than. There's two particular kinds of methods that I talked about: stochastic Galerkin finite element methods, polynomial type approximations. They can be very efficient and much quicker than standard sampling methods, as long as the number of input parameters is relatively low and the solution is well behaved enough. And then the final thing that I talked about, building surrogate models using reduced basis ideas, they can also offer some time savings, but only if you can invest enough time in building the reduced basis in the first place. Okay, so if you'd like to know more about any of those methods and the last 2 points in particular, there are some references in my slide, and I'm happy to make them available. And that's it. Okay, I'm happy to take a quick question, but you're all probably gagging for a cup of coffee. So I'm around all day if anybody wants to ask me questions, and I'm happy to answer any questions in the discussion session later on as well. So I suggest we break now for coffee and reconvene at 12 o'clock. No, is it?
My program's on the next
10 to 12. Okay.